In symmetric cryptography, the primary objective is straightforward. Take a plain text message, X, and send it across an unsecure communication channel. To prevent interception, we apply a specific key, K, transforming that plain text into a secure ciphertext, Y. For many centuries, the standard for this encryption was the substitution cipher. The mechanics are simple. Take one letter of the alphabet and swap it for a fixed alternative. If you scramble the English alphabet completely, the number of possible substitution combinations is 26 factorial. Expressed as an exponent, 26 factorial is roughly 2 to the 88th power. That is the key space, the total number of possible keys an attacker would have to guess. Modern short-term symmetric encryption schemes often rely on a key space of 2 to the 64th power. 2 to the 88th is massively larger. Attempting to crack it by guessing every single combination would overwhelm contemporary computing power. Yet, any beginner can break a substitution cipher by hand in a matter of minutes. The vulnerability exists because the substitution cipher encrypts letters rather than abstract data. It scrambles the characters, but it perfectly preserves the underlying linguistic properties of the plaintext. This chart visualizes the letter frequencies in the English language. In any standard text, letters do not appear at random, uniform rates. There are distinct statistical outliers. The letter E makes up approximately 13% of all characters in a typical English sentence, followed by T at roughly 9%. When you apply a substitution cipher, you only swap the labels. The shape of the data remains untouched. An attacker does not have to guess 2 to the 88th power keys. They simply count the characters in the ciphertext. The character that appears 13% of the time is E. Mapping the highest frequencies to E, T, and A immediately unravels the cipher. The massive key space is bypassed entirely through statistical analysis. This failure illustrates Kerckhoffs' principle. A cryptographic system must remain secure even if the attacker knows every single detail of how the algorithm works, missing only the key itself. To meet that standard, cryptographers had to abandon linguistic tricks. Secure encryption required moving away from letters entirely and rebuilding cryptography on the rigorous, bounded mechanics of discrete mathematics. Modern encryption algorithms cannot operate on infinite continuous numbers, fractions, or decimals. They rely entirely on discrete, finite sets of integers. The foundation of this system is basic divisibility. We state that a non-zero integer b divides another integer a if a equals m times b, where m is also an integer. This perfect division, written as b divides a, means there is absolutely zero remainder. But the core mechanics of cryptography rely on what happens when the division is uneven. This introduces the division algorithm. For any integer a divided by a modulus n, we yield an integer quotient q and a remainder r. Mathematics places a strict boundary on this value. The remainder is always greater than or equal to 0 and strictly less than the modulus n. It cannot be larger than the number dividing it. In cryptographic math, the quotient is discarded. The focus shifts entirely to the remainder, which acts as the core output used to define a specific position within a fixed, predictable range. Focusing exclusively on the remainder creates a mathematical structure known as modular arithmetic, which operates within an integer ring, denoted as Zm. This structure takes a standard infinite number line and bends it, connecting the ends to form a closed circular track with a finite set of discrete integer points. Applying the division algorithm here, the quotient q simply dictates the number of full rotations around this circle, while the remainder r dictates your final exact landing position. This leads to a formal property. Two integers a and b are said to be congruent modulo n if their remainders are the same when divided by n. Mathematically, a is congruent to b modulo n if the modulus perfectly divides the difference between the two integers. Operating within this ring offers massive computational advantages. By applying intermediate modulo reduction, calculating the remainder at each step of an equation rather than at the very end, we prevent values from exploding into unmanageable sizes during complex calculations. No matter how many additions or multiplications occur, the resulting data is guaranteed to remain securely bounded within this finite set. The values never exceed the set limits, ensuring the software systems executing the cryptography never encounter an integer overflow. Scrambling data through addition and multiplication within an integer ring handles encryption smoothly. However, encryption is pointless if the authorized receiver cannot reverse the math to decrypt it. To reverse multiplication, we normally use division. But standard division does not exist in modular arithmetic. Instead of dividing, we multiply by a modular inverse. The inverse of a multiplied by a modulo m results in 1. This relies on an absolute wall. An inverse exists only if the greatest common divisor of a and m is 1. When two numbers share no positive integer factors other than 1, they are defined as relatively prime or coprime. If this coprime condition is not met, the inverse simply does not exist in the ring. Without an inverse, decryption is mathematically impossible, and the encryption becomes a one-way operation that permanently destroys the original data. We can observe the direct impact of this rule by applying it to the Affine cipher, an encryption scheme that utilizes both multiplication and addition. In the Affine cipher, ciphertext y equals ax plus b modulo 26. To find a valid key a, its greatest common divisor with 26 must be 1. Eliminating all even numbers and 13 leaves only 12 valid coprime keys out of 26. If a cryptographer ignores this and chooses a non-coprime multiplier, multiple distinct plaintext letters will output the exact same ciphertext letter. The data collides, and the decryption fails. This precise restriction on the key space stands in stark contrast to the naive assumption that 2 to the 88th combinations automatically provide security. Modern cryptography relies on the uncompromising application of discrete number theory. Through the strict use of integer rings and coprime constraints, engineers ensure that sensitive data remains perfectly bounded, statistically flat, and, crucially, mathematically reversible.